Hello and welcome to this University of Southampton ECS outreach video. My name is Joseph Earley and I'm a first year PhD student in the Agents, Interaction and Complexity group. I did my undergraduate and master's courses at the University of Southampton on the MEng Integrated Computer Science course. In this video I'd like to talk to you about a coursework I did in my final year of university. Hopefully it will give you an insight into what you can expect towards the end of your degree. So the module I'd like to talk about today is deep learning. So the deep learning module is typically done in the third or fourth year of your degree, and it builds upon the skills that you've learned through the earlier years, such as machine learning and the essential mathematical skills that are crucial for a computer scientist. It's a very research-driven module, and by this I mean the people who are teaching you in lectures, setting the coursework, running the labs, really know what they're talking about. They are doing this stuff day in, day out, and attending conferences worldwide, publishing their research. As a student, this means you're getting to use real state-of-the-art techniques on real data sets, solving real problems, which is going to set you up perfectly if you're going into this kind of thing either in industry or research after you finish your degree. The coursework for the deep learning module was all based around reproducibility. The idea of reproducibility is that if one person does an experiment, they can share their methodology and results, and hopefully other people will be able to redo the experiment and get the same results. In theory, for computer science, this should be easy. We can share our code online and other people can download and run it. However, this begins to fall down when you consider that people might want to rewrite the code in a different language, or it might not even run on their machine. There's the iClear Reproducibility Challenge, which is effectively an open call asking people to try and re-implement and reproduce the results of existing research. For the deep learning coursework, we were answering this call and were asked to take a recent deep learning piece of research and try and re-implement it ourselves. The output of this was then to write a report detailing what was reproducible, what wasn't reproducible, as well as sharing our code so other people could look at it and potentially take it further. So when I did the coursework, my team and I chose to re-implement the research titled A Learned Representation for Artistic Style, published in 2017. This research revolved around style transfer. So that is when you take a content image, a style image, and you extract the style from the style image and apply it to the content image, such that the image is re-rendered in such a way that it resembles the style of the style image while retaining the content of the content image. So as you can see here, there's a picture of a boat combined with a picture of a woman wearing a striped dress, and then the result is the same picture of the boat but redrawn in such a way that it has elements of the style from the reference image. So this goal of style transfer can be achieved by using a deep learning technique known as a convolutional neural network. This is realized in the form of a transfer network, which takes in our content image and then re-renders it in the style that we want. The way the transfer network works is that it has a bunch of internal parameters that initially start randomized, and then over time, the software tunes them such that we get the result that we want. And it does this by training on two losses, a content loss and a style loss. So the first, the content loss, ensures that the stylized image retains the original content features of the input image. And by this I mean the various shapes and structure of the image, the boat, the bridge, the sides of the building, etc. The second loss, the style loss, is then a measure of how close the stylized image is to the style input image that we want to try and emulate. So this is looking at things like color and texture, and the overall kind of artistic style, whatever the network learns that means. So these are just mathematical functions that just in some way compute the relevant bits we're looking at. And by minimizing these over time, the transfer network learns to produce the stylized image as we want. The actual contribution of the research that we were re-implementing was to take style transfer, which had previously been published, and adapt it and extend it to become end-style transfer. In this scenario, the transfer network has been adapted so it can learn multiple styles. So a small element of the transfer network becomes kind of extracted and is made particular to a single style. This means you get these kind of so-called style blocks, which represent different styles, and you can swap them in, swap them out to the transfer network, depending on what style you want to transfer to. The remainder of the transfer network remains the same. It's just these small blocks that you can trade in to swap the kind of style that you're rendering. Everything else remains exactly the same. But this means that you end up with these style blocks that essentially are small elements of the network that represent the particular values for a style. Essentially, it's just a long vector of numbers that in some way, in some sense, represent the features of that particular style. The advantage of having transfer networks that can do multiple styles is that you can begin to do style interpolation. By taking the style blocks that represent different styles, you can actually interpolate between the two different blocks such that you produce a entirely new style that is representative of the two other styles. And you can weight this such that it's more of one or more of the other. So here I show two examples, the first of which is a two-style network, so it has learned two different styles and it interpolates between the two, where the left-hand image represents completely style 1, and as it transitions across to the right, the interpolation becomes more weighted towards style number 2. But you can extend this beyond just two styles. In fact, you can do many, many styles. We went up to about 16 when we did the work. Here's a representation of what it looks like with 4 different styles, where each of the most extreme corners represents just that particular style, and then in the middle represents a complete weighting of all of them, and everywhere in between is the kind of the relevant weightings for the interpolation. So as you can see, the interpolation is pretty cool and it works really well in terms of transferring from one style to another, and that was kind of the main contribution of this research, was showing that this is possible to have a transfer network that learns multiple styles and then interpolate between those styles to produce something that is entirely new. The main goal of this coursework was reproducibility, and to this end the output of the coursework was to share a report online and also make the code open source and readily available to anyone who wants to take a look at it. This meant uploading the code to GitHub and making it an open source repository, and then also writing a report detailing the specifics of our implementation, what we did manage to gain from the original paper and what we kind of had to work out for ourselves, i.e. a measure of how reproducible the original research was. And that also included a comparison of our results to the results of the existing research. I actually went a step further with the coursework in my own time, just as an extension to what we managed to implement. And I chose to wrap this up, the kind of style interpolation, in a web app. So here you can see I've trained a network with 5 different styles, and you can upload any kind of content image that you want. And then in real time, you can interpolate between the different styles to get a rendered stylized image that represents the interpolation based on these sliders. So basically I utilized the skills that I'd learned in the rest of the degree to produce this and kind of package it all up in something that's quite nice and I could share online. You can see here the interpolation style slider being changed and the relevant style coming more into the content image than the other ones. And here I'm demonstrating that you can actually use any content image. That's the way that the style transfer network has learned. We trained it on lots of different images such that it can stylize any kind of input image, not necessarily one it has seen before, and that the style transfer works in exactly the same way as in the previously shown figures and demonstrations. So I'll let this play for a little bit longer so you can kind of see what it looks like. So here I had 3 styles fully utilized, and then I'm reducing one of them. And you can see those elements of the style begin to fade from the image until only the 2 other styles are retained. And then I'll reduce it down to just one single image so you can see the interpolation in effect. So that brings me to the end of the demonstration of the deep learning coursework. As a few closing remarks, I'd like to say that deep learning is an absolutely fantastic module. It's probably my favorite module that I did during my integrated master's course, and specifically the coursework was really fantastic to do. I actually wrote up kind of what I've vaguely summarized in this video in a more detailed article, so that's available online. The link's at the bottom of the slides. And just as a general note on the computer science course that I studied, it was really fantastic, and I hope this has been an inspiring video and given you a flavour of what it can be like towards the end of your computer science degree. Thank you very much for watching.